Hi, everybody. This is Mr. Folly, and welcome to Podcast 1.1, where we're going to talk about things that are mixtures. We're going to talk about things that are pure. We're going to touch just a little bit on measuring because, believe it or not, there's something that we're still pretty bad at, and we're going to talk about separating mixtures. So let's hop to it. Physical changes. Okay, so physical change is a change in mass or shape, but not identity. So examples of physical changes would be cutting something, boiling something. Now notice if you boil something, you might go, hey, water looks different than steam, right? But whenever you do a phase change, the formula for water is H2O, and the formula for steam is H2O. So notice how you're not changing any of those things. Same's true for boiling or freezing. Molding something, what I meant for that was something like this. So if you craft something into a different shape or something like that, it's still the same substance. Okay. So if I dump boiling oil, oh no, it's going to happen to me again. So if I dump boiling oil on people, that oil, even though it's changing shape, is still the same chemical substance. And if I put whatever this is, we'll say it's chalk or something, melted chalk, and then make a cast of it, the same thing happens. It's still the same chemical substance. Chemical substance changes the identity after the change. It has a new chemical formula. So example, if H2O turned into H2O2, that is a new substance. Water, drink it all the time. Ooh, drink it, you die. Okay. Words that indicate chemical changes are burn, die, precipitate, form a gas, change a color. I'm actually going to hop back one and add a word on here. Distill is a physical change, and filter is another physical change. So, oh, look at that, it's 7:45. Burn, die, precipitate, form a gas, change a color. All of those are chemical changes. Now, a cautionary one, boiling forms a gas, but it is not a chemical change. Okay, so watch out for that one. The other one is a precipitate, is where you mix two liquids together and chunks form. So maybe you remember that. It's pretty cool. We've done demos of it in Chem 1. But you mix two liquids together and chunks form. All right. So burning something, notice how burning typically forms a gas. If something changes colors, that's why I have leaves on here. That's an indication of a new substance. If you burn Freddy Krueger's face, he comes after you in your dreams, and his skin is not regular skin, it has different properties. Here are substances. Elements, they're one type of atom, and it can be diatomic, and you need to memorize your diatomic elements as, I don't know, I'm doing this way. I always do it in off Fulbright H. So nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and hydrogen, or I suppose I said I always do that, or uncle breath. So what that means, these are like Siamese twins, so they're always stuck together when they're all alone, okay? So you will never, 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 never see N all by itself. So like I could have iron plus nitrogen. Now this will never look like this. Iron is a 1 all by itself. You'll never see this and then get like Fe3 and 2. You'll never see this. It has to be a 2. So what the reason why is they're so attractive and reactive that they'll bond with themselves if nothing else is around. One type of atom will, when we draw pictures of them, might be a box, but if it's diatomic, not that it has to be a circle, but it will be touching each other. Compounds are more than one type of atom, so an example there would be a circle, square. Touching represents a bond. Okay. Um, and they are not a combination of properties. So hydrogen, for example, hydrogen is kind of explosive. Oxygen supports burning. You know, that takes oxygen to burn. Oops, I misspelled burn. Supports burning. But water puts out a fire, right? Sodium, if you put it in your mouth, will light on fire and produce hydrogen and all those bad things. Chlorine, if you breathe it, will react with your lungs and kill you. But if you eat salt, it's necessary for a healthy diet, but not too much. Oh, no. Salt is a good thing. Oh no. And now my screen's gone. I can fix this. Mixture. Any state in any state is possible. Okay. So there are two main types of mixtures. One is homogeneous. Homogeneous is synonymous. It means the exact same thing as a solution. Okay. Every sample is the same. So that means if I have a big beaker of it, if I take a sample from here, or here, or here, or here, or the top, or the bottom, or the middle, every sample will be the same. Okay? So like if you take a drink of Coke, it tastes the same the first sip as the last sip. Heterogeneous, the samples are different. Living things are heterogeneous. Um, so salad, grass, 18 karat gold. Oh, by the way, salt, here's samples. So solid is whoa. Salt water is homogeneous. Because every sample would be the same. When you drink it, they're all just as salty. Some of you might say there's layers of salt in the ocean. Yeah, but if I just have salt water. Salad is heterogeneous. Man, this bite has a lot of carrot. Man, this bite has a lot of dressing. It's not the same. Grass is relative to its size. So it can be a homogeneous mixture. Mr. Joe has the best grass. It's all made of Pennsylvania bluegrass. That's crazy. Um, so it's homogeneous at that level, but when you look at it under a microscope, it's heterogeneous. I remember that. Each grass cell has a cell wall and it has a nucleus and it has, yeah, so you get that's got those things, different parts. 18 karat gold is an alloy and all alloys are homogeneous. 18 karat gold is gold and zinc, so it is a mixture, and every sample is the same. All right, so just looking at a couple of these, this first one is a pure element, and it's a gas. There's only one type of circle. The next one is a heterogeneous mixture. The reason it's easy to tell it's heterogeneous, boy, that's not a very straight line. If I drew a line right there, the top part is Mickey Mouse's, and the bottom part is triple dots. Okay, so it's a heterogeneous mixture. So I want to make sure that you know that if you see something in layers, it's heterogeneous. And it's of an element. This is a triatomic element. There aren't many of them. That's probably ozone, which is O3, a very rare triatomic element, and a gas. And I said that the Mickey Mouses were gases because they're floating up on top, and there's some space in between them. I said that the triple dots are liquids because they're kind of shuffled around and they're compact. C, really hard to tell if it's homogeneous or heterogeneous. So if I give you a test question like this, you have to explain why. So what I would do is I would cut it into 4 and go, okay, look, we've got, I guess it's heterogeneous because the bottom right one isn't in there. But you get the idea how it's really hard to tell. It's 2 elements because there's just a little circle not touching anything and a big circle not touching anything. E is a pure compound and it's a solid because it's a compound because they're touching. The ears are touching the face on the Mickey Mouses. And it's a solid because they're organized and they're the same all the time. Notice the difference between the dots and that. The shufflingness of B makes me think it's a liquid. F is a solid. It could be a liquid as well, but pure compound. Ooh, I put pure compound. No, F. I put duh. So duh, it's an element, one thing. And it's a solid or a liquid. You can't tell with circles. G is a pure diatomic element, and there's not an H. But note how hard it is to make homogeneous samples all identical. So that sample thing's hard to do. How to measure. All instruments have a numbered, an unnumbered, and an estimation. Okay, so that means that this right here is 0.0. This digit right here is estimated by the digital substance, and it will lock in a place. When digital balances first came out, it would continually flicker in the last decimal place. So um, if I took Sammy's toenail and it weighed 0.83 grams, it would say 0.83, 0.82, 0.82, 0.83. You keep flickering back and forth. And because people are dumb, and I can't say I wouldn't have done this the first time I had it, they sent it back and said, your balance keeps changing back and forth. So what it did was it would just pick one and lock it. And it just guesses. And what that means is it's within 0.83, 0.82, if I were to draw a line, if I said, what's the thing right here? You need to say, okay, I got the wrong glasses on here. 5.4, and I need a little more, 5.42. So notice how you need, um, let's see, and of course my line disappeared. Just to make my life difficult. You need that last decimal place that most people would agree on for a little bit. It's definitely closer to the 4 than it is to the 5, so 5.42 is a better answer. This one just I put a picture of graduated cylinder. It's a really bad graduated cylinder. All right. Separation by boiling point. You may have to draw this or understand this. I've got a mixture right here. Heat it up. The things that are not very attracted to this stuff are going to come up through here. They're going to boil first. And as they come up here, they're going to get pushed down here. So there's cold water running through it, which will then cool it off. See how it makes little drips? Drip, 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 blah, blah, blah. Okay, so if this is, now I'm a little colorblind, so I might have these colors wrong, so feel free to laugh at me. If this is blue and this is purple, the mixture is blue, the purple stuff comes off, and it leaves something. So it's separation by attraction. Blue is very attracted to itself, so it didn't boil. Purple is less attracted. So if it's less attracted, you're able to leave. So those of you who are seniors and you don't like it here in the wonderful world of Lyons Township, you might go to school very far away. My brother was like that. We grew up in Elkhart, Indiana, and he went to the farthest away school he could go to for free. He went to the University of Houston because it was far away. He's not attracted to the great state of Indiana. But most everybody who grew up in Elkhart, Indiana was very attracted to Elkhart, Indiana, and stayed there. So my brother would be less attracted to it or less attracted to it. You might have to draw or interpret a picture like this. You do not need to use the words retentate and permeate, but you can see it's a little guy fit through the holes. It's a big guy, doesn't fit through the holes. And this shows one layer of filtration. Frequently, things like the masks that we're dealing with now with COVID has more than one layer. So it would be a little better than that. And I watched a video that was pretty cool about how they charge these, put electrical charges on them. So a little bit we know about intermolecular forces. Um, the world knows a lot. As you know, first day 2 AP chemistry students, we don't know much. This will have attractive parts to it. So stuff like we talked about how the intermolecular forces are strong over here. It doesn't boil as much. If you put forces on here, intermolecular forces, you're more likely to get those things to grab and get stuck. Okay. Masks don't really have that retentate kicking out part, but you get the idea. Separation by chromatography, which is separation by polarity and size. So instead of polarity, I wish I had said, polarity is not wrong. I wish I had said intermolecular forces. So intermolecular forces include polarity, and polarity is like the charged part of each particle. Okay. There are 2 types of substances, polar and nonpolar. Polar has charges and will stay with other polar things. So, like, if you really like people with blue hair, you'll probably hang out with people with blue hair more. It's kind of how it goes. So, being polar is like having blue hair, I guess. Again, I'm colorblind, so all hair is equally blue to me. Polar paper means polar parts move slower. So if the paper is polar, right, then whatever this ink or dye is going to be so attracted to the paper, it's not going to leave. Okay. So like if you're at a party and everybody's like outrageously attractive, you're going to stay there longer. So polar solvent, which is the liquid, most often water, but doesn't have to be. So polar solvent and nonpolar paper means that the polar parts move faster. Polar, sorry. Okay. So, and when you measure it, so in this part right here, notice you measure the top of the dot. You don't measure the middle of the dot. Okay. So, and I looked a couple of different places. This slide right here says find the average of it. The last source that I saw said measure the top of the dot. So notice that's a big dot. So. All right, so what happens is you basically get yourself a beaker, you hang your paper, your chromatography strip, and that's it'll be a pencil. And it'll be a coffee filter, and the water level would go below this. And what happens is there's a dye, point of application would be a pen, and then you would get a blue dot, and then you would get like another red dot. And these would be a mixture of blue dye and red dye. Okay? I think we've done chromatography before. You do it in middle school a lot. Thin layer chromatography is the same idea. The polar stuff is attracted to the polar stuff. The non-polar stuff is not very attracted, so it moves. It stays with the non-polar stuff. There's a thin layer on a sheet of plastic. The layer is typically silica, which is a very polar OH group on the edge, or alumina, which is also very polar. So remember how polar likes polar? That means that polar things move slowly. So it's exactly the same besides that. So instead of going on paper so much, it's on this thin layer chromatography. Some dyes and some mixtures, you can't see it. So what you do is use UV light, ultraviolet light, and you can see invisible spots. So thin layer chromatography can be used to see spots that are not in the visible light spectrum. You can also let it run for a while, and then you can spray it with something that will cause them to show up. So for amino acids, you do the same thing. You drop it in the little dude, like drop it in water, but you can't see anything move because it's not in the visible light spectrum. And then after 20 minutes, you spray it with ninhydrin for amino acids, and then it will show up because if you are an amino acid, ninhydrin makes you change the thing. So M is the sample here. So M is my sample of protein. Amino acids make a protein. What amino acids are in M? This is thin layer chromatography. So you put it in there, you wait for 20 minutes, it's like, oh, it didn't work. Then you spray it with ninhydrin, and you see probably 3 or 4 different colors. So this dot and this dot are both right here, so 5 is in sample M. This dot and this dot are so close, if you don't think they're the same, you're a little too uptight in this tough time. So 1 is in it, and then this dot and this dot are close enough, so I would say it's 1 for it. That's it. That's how hard chromatography is. Column chromatography. Okay, so I found out that I did not, column chromatography has not been on the test, but I found out that I misunderstood it before. So you have silica or alumina, gel and the burette. So again, super polar. This will not move. Think sticky goo. So imagine there's sticky goo that stuff can slowly pass through. Okay, or think of it like a forest or a jungle with a bunch of sticks you got to kind of wind your way through. There's steel wool at the bottom to make sure the goo doesn't go out. Now, what you put in here will go out, but the goo will not. See, steel wool, steel wool, steel wool. It still has solvent, and it separates. What happens is you pour your mixture on top, and you're going to keep pouring more and more and more and more water. So you're going to pour water in it, and some of it will separate. Pour more water on it, some of it will separate. Pour more water on it, some of it will separate. Pour more water on it, some of it will separate. The yellow is less polar than the blue because it travels farther. You can collect the yellow. Dun, 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 we're done. Physical changes stays the same thing, same formula. Chemical changes change the identity, and they have new physical properties. Know distillation, chromatography, and filtration, how to do it. Know that they're physical changes. Know elements and compounds and mixtures by picture. If things are touching, there's a bond. And know that AP Chemistry is a great place to be.